Hello everyone, can you hear me? So, short introduction, my name is Katy, and I'm here to talk to you today about refactoring, or, well, generally about legacy code. And I'm sure most of us here have dealt with legacy code at some point or another. And we're going to talk about testing and refactoring that code. Right, first of all, legacy code, what exactly is it? There are quite a few definitions for legacy code, and I think the one I like the most is legacy code is any code that you didn't write just now. It could also be code that came as a result of incorrect assumptions. So when people are writing code, you often start off with a set of assumptions that as your code evolves and develops, turn out to be incorrect, and you end up with mess that doesn't work anymore and doesn't make sense anymore. Code that is built using unsupported technology, so something that you can't really update anymore, maybe isn't secure anymore, isn't following best practices anymore. And also, finally, code that isn't tested. And what is refactoring is something we're going to talk about today. Refactoring is changing the existing code without actually changing any of the underlying logic. So you want your application to function in exactly the same way as it did before, but you want your code to be better. That might be to improve the code structure or to implement new technologies, and it's usually done in small and incremental steps. You'd refactor to improve developers' understanding, which increases developer velocity, which means you can develop faster. It increases the application performance if you approach the same problem from a different angle. You can use it to introduce new technology, as I said. If you're running legacy code on outdated and unsupported technology, refactoring is a really good tool for upgrading, and also to accommodate changes in product requirements. Unit testing. I'm specifically going to talk today about unit testing, which is a way of verifying that each individual piece of your code is working as intended. A unit is generally, a definition for a unit would be a piece or component part of your code, which some people look at as being functions, so each function or each method is a unit, but you could also argue that each set behavior is an individual unit as well. And unit testing is not a substitute for other types of testing. There are various types of testing. There's integration testing, acceptance testing. Unit testing is just one way of testing your application, but I find it's very important, especially when dealing with legacy applications that you need to refactor. Why would you unit test? My favorite reason for writing unit tests is because it documents your application. It says exactly what your code should be doing. It also helps prevent regression. So if you make any changes to your code and you break something unintentionally, a failing test will alert you to that. You can also test integration with new technology. When you upgrade your application or you use a new library, unit testing will help you determine whether or not it's working as you expect it to. And it also validates product requirements. Again, that sort of links in with the documentation aspect. You know exactly what your system is supposed to be doing and that it's doing it correctly. So, when it comes to unit testing and legacy code, there's often a paradox where you can't refactor the code because it's untested, and it's dangerous. You don't want to accidentally break anything, but by the same token, you can't actually test the code because it's not refactored yet. It's untestable. So this is a situation that developers often find themselves in, and I'm sure that you have all found yourself in a similar situation. Who's been tempted to do this? Hands up if anyone has seen a legacy code base and just gone, you know what, just going to rewrite this, right? I can't deal with this anymore. Yeah, no, don't do that. That's a trap. First of all, because when you start rewriting a code base, you actually need to figure out how the old code base was working in the first place. So you need to figure that all out and probably test it anyway. A better solution, in my opinion, would be to perform just enough refactoring to make your code testable. This is probably going to result in a few weird shortcuts that I'm going to go into later. But once you've got the testability, you can add your test coverage. And once something is covered with tests, you can refactor the code and indeed profit. I'm making a few assumptions during this talk. I'm assuming that you're at a PHP conference, you're developing with PHP, and you have access to a terminal, and you are using Composer, the common dependency management system. I'm going to introduce you to our tools. So our main tool for this is PHP Unit. That is probably the most well-known unit testing framework for PHP. And if you're really working on legacy code, you might think, oh yeah, but I can't use that newfangled modern stuff. Well, although the version 5 of PHP Unit is unsupported, it does still support, there is a version that you can use of PHP 5.6, so if you're not quite on PHP 7 yet, don't worry, not all hope is lost. I recently upgraded a large application from PHP 5.6 to 7.1 so far, and unit testing really did help. To install PHP Unit, it's really simple if you're using Composer. Composer require --dev. That prevents PHP Unit being deployed to your live application, which is not necessary. And then the PHP Unit, and optionally you can specify a version that you'd like to use. And then when you do vendor bin PHP Unit version, it will give you version information. So as a definition of a unit test or an example, this is an anatomy of a unit test. Each unit test or group of tests is a class which must extend the PHP unit base test case. So this is a demonstration of testing some function that returns true. We have our function, which is aptly named test some function, because some function is the function we're testing. In my slides, I have underlined the functions that we are testing so that you can tell. And the result of this function should be true, which is why we're using assert true. And that's a general gist of a very basic unit test. And to run your tests, just at top right, I've put the file name and directory that my tests are in, just so that you can understand the structure. So I decided in the course of this to put all of my tests inside a directory called tests. And to run our tests, we simply use vendor bin PHP unit again, which is the PHP unit executable, and then specify the directory that we've put our tests in, which is test. And that's what you should end up with. The function should return true, and you get a nice passing test. Hooray! And that's the command that you're going to be running again and again and again and again and again and again as you test your application. A second tool that I want to introduce is Mockery, which is a mocking framework for which you can integrate with PHP unit. Mocks are basically test versions of various that you can make test versions of the dependencies of your code. To install it again, Composer required --dev mockery to prevent it from being installed on your live application. And this is an example of how you might mock a dependency. So our dependency here is the object class, and you can simply do mockery mock and then create a fake version of that object. You can also perform expectations on it. So you can create a mock object, and you can tell it that at some point during the execution of your test, it should receive the method. And when it does do that, it should return a specific value, which is really handy, as we will find out later. Also, something to note when using Mockery is that you have to close it. So PHP unit offers a setup and a teardown function. So in every teardown function, you need to put Mockery close, otherwise it will not count your expectations. So just a little bit of a warning when it comes to using something like Mockery. Mock your dependencies, but only when you have to. Don't mock everything just because you can. Your units don't exist in isolation from the rest of your application. So if you mock everything, you're testing only the very specific units and not how they interact with the outside world, which can result in tautological tests. Something passes because you've told it to pass, not because it actually would pass. And especially, and it's very tempting, don't mock the thing you're trying to test. So if you're trying to test class A, don't make a mock of it. Don't even make a partial mock of it. You'll enter dangerous territory and end up again with test passing because you've told them to pass and no other reason, really. So I'm going to go through a bunch of examples of what you might find in legacy code and how we might refactor these things. The examples I'm going to provide are deliberately simple. You might not find something exactly like it in your code base, but I want to provide you with building blocks that hopefully you can go through your existing code bases afterwards and see where you can apply all of these techniques. There's quite a lot to go through, and there are some things that I will have missed. So please come and find me afterwards if you think there's something that you've encountered that's been difficult to test and you're not sure how to go about it. I'm gladly help you. So our first scenario that we might encounter in our legacy code, and one that I still encounter quite often, is output interference. I'll explain what I mean by that. If we have a method that echoes something. So this method is called yodel, and if you pass it a tune, it'll yodel the tune, it'll echo it, and you'll print it to the screen. And if you don't send it anything, it will present a default echo. So these kinds of outputting in methods is not something that's particularly helpful most of the time. It demonstrates a lack of separation of concerns. You're within your code dealing with the presentation layer. You're actually outputting something to the screen, or in the case of unit testing, you end up outputting it to the test run. So if we did want to test this method, we'd create our new printed output test, and we've got two potential branches. So we've created one test for each of the potential branches, the plain yodel and the echoed yodel. And I've put in comments what we expect the output to be. And then we run the tests, and we get the output in our test runner. That's not particularly helpful. It's pollutant, and imagine if you have something echoed that's quite large, like, for example, an entire page. That's going to be frustrating. And they're also risky tests, because you might have noticed that in these tests we haven't actually asserted on anything. The function itself doesn't return a value, it just echoes. So how are we supposed to test that it echoes the right thing? First of all, we're going to prevent the output from being dumped into the test runner, because that's really confusing. We're going to capture that output, and when we've captured it, we're going to perform our assertions on that output. How do you capture output? Well, Picture has this amazing thing built in. It's the output buffer, or OB, and before you run any methods that echo anything, you should start the output buffer. Then, after you've run the method that does all your echoing, you can stop the output buffer. So everything that is echoed is being captured by that output buffer. And you can get those contents by using OB get contents. And now we have something that we can actually assert on. We've got our output. It's no longer in the test runner, and we can perform some assertions on it. So in our test yodel, we can now do this assert equals and it works. Hooray! The test it works. Our code, our echoing function is now tested, and you can go ahead and you can refactor that to your heart's content and maybe take out the echo eventually, but remember you will have to refactor your tests. And for our second, this is our second echo yodel, so this is our second branch of the yodel method, and again that works in the same way, capturing the output and asserting. Our second tricky test scenario, and I think this is probably the one that is going to cause you the most pain, and probably the one that you're going to encounter the most often, and also people find the most daunting. Hard-coded dependencies. If you're working with legacy code, it's quite likely that there will not be any kind of dependency injection. It sounds difficult to implement, but it's actually really simple. So anyway, one version of this hard-coded dependency is a static method call, and this is the reason why many people will tell you that static methods are bad. So sorry to anyone that doesn't know Dragon Ball Z or the over 9,000 meme. Yeah, just bear with me. So in this example, we have a method called getPowerLevel, and in our method, we are calling the power level of the Goku class, Goku being a character who has a power level. And we want to, we're scanning him, because we're the G-Jump, we're scanning him, and we want to know what his power level is. If the power level is over 9,000, producers can go, it's over 9,000! And if it's not, well, then we can assume that Goku is being suppressed right now. So we have our two tests, because we've got, again, our two branches. We've got the it's over 9,000 branch, and we've got the suppressed branch. So we want to get the result and get the power level. We want to test the under 9,000 and the over 9,000 things. But unfortunately, currently, Goku, it always returns 5,000. Goku's power level is always going to be 5,000. So looking at our tests, well, the under 9,000 probably is going to be quite easy to test, but the over 9,000 is not going to be easy to test because Goku is never going to return over 9,000. So this is our under 9,000 test. We can assert that the result of getPowerLevel is suppressed because the static method is going to return 5,000, it's under 9,000, it's suppressed. When we test stay over 9,000, it's going to fail because it's not, it's 5,000, and that's clearly less than 9,000. So this is where mockery comes in. We're going to create a new mock of Goku. We're going to create a new test version of Goku using a mockery alias. We're going to set the return value of Goku's power level, to be 9,001. And we're going to have to run the test in a separate process. This is because with mockery aliases, once you create a mock, it completely overrides that class. So if you try to reuse it, it will throw up an error, oh, this class is already defined. So we have to run each of our tests in a separate process. Anyway, I'll explain how to do that in a second. So this is how we would create our Goku mock. And use a super saying Goku now, and because power level is going to be over 9,000. You see mockery mock and the alias colon Goku. So alias is saying this is an alias of class. I'm not giving you an object, I'm telling you to make this class. The class should receive power level, and when it does, it should return 9,001. And this is our run test in separate process annotation. So PHP unit has a series of annotations that you can use with your tests to specify the behavior of some of your tests. So by putting this annotation before the definition of your test class, it will run each of the tests in a separate process. This does slow down your testing, but these are the sacrifices we have to make in order to get legacy code tested. And now we have our Super Saiyan Goku, and he's returning a power level of over 9,000. We should indeed assert equals, it's over 9,000, and yay, it works. So that's that. There's another type of hard-coded dependency, and this is it. When you're actually creating a new instance of a class directly within your methods. So I don't know about you, but my outlook tends to depend on the weather. When it's rainy, I'm sad, and when it's sunny, it's good and cool. So like my outlook depends on the weather, the outlook method also depends on the weather. The outlook method has no influence on the weather, but nevertheless, it requires it in order to perform its function. That is the definition of a dependency. And it's hard-coded because it's creating the dependency itself. It's not being given it from anywhere else. So how can we deal with this hard-coded dependency? Or let's have a look at what it is. No one can predict the weather. I mean, the meteorologists try to. It often doesn't really work. And in the case of our weather forecast class, similarly, it can't predict the weather either. In fact, it just returns true or false. It's completely random. And we have two outlooks on life as a result of the weather. Our glass can either be half full or half empty. So we've created our outlook test, our test class, and we've created our two methods as the two branches of our test. The first one would like to test whether our glass is half full, and our second one is would like to test when the glass is half empty, and both rely on the weather either being sunny or not sunny. If we remember our weather function, it's random. So when we try to test half full, we get the outlook and we assert that it equals the glass is half full. That only works when it's true. And this is our test half empty, gets outlook, and when the weather is not sunny, it should return the glass is half empty. But they're unreliable because no one knows what weather's going to return. It could be true or false. Half the time, the tests are going to run and they're going to pass. Half the time they're not. One might pass, the other won't pass. Who knows? So how do we deal with this situation? We are going to, again, invoke the powers of mockery. And instead of using an alias, we're going to use an override. So an alias creates an entire new definition of the class and is used for mocking public methods, public static methods. Override intercepts a class when you create a new instance of it. And because our function is creating a new instance of a class, that is why we are using an override. The mockery documentation explains it a lot better than I could, so go check that out. And then once we've got our overridden mock weather forecast, we're going to force the return value to be true or false. That way we can run our tests for glass half empty or half full, and we can perform our assertions based on that mocked return values. Again, we kind of have to run our tests in a separate process, because when you create a mock and you intercept a class, it's always going to intercept a class, and you can't reuse that mock. So first of all, we're going to do our mockery mock overload and then give it the name of the class. Then we're going to say it shall receive get weather. Actually, I think the method is sunny. I should have been on the slide. And we're going to force it to return true. So when we do run get outlook, it's going to go and get the weather, it's going to be sunny, and it's going to be true, and our glass is going to be half full. And we can run the same thing for it not being sunny. We can force the return value to be false, and it's going to get my outlook, and the glass is going to be half empty, because I hate the rain. With our annotations, again, running tests in separate processes. Hooray! There is a problem with running the tests in separate processes. It's slow, really slow, painfully slow. I think we were using a lot of aliases and overrides in our code bases, and once we managed to refactor them all out, our build time went from 20 minutes to 10. So if you've got a lot of tests, it's worth avoiding them. So we're going to look at refactoring these hard-coded dependencies. And it sounds really daunting, but it's not. Dependency injection is really important. It's not as hard as it sounds. I will explain it. All will be revealed. You will no longer be mystified by this terminology, dependency injection. And then once we've got our dependency injection set up, we're going to mock our dependency. And we're going to inject it, because a dependency injection is dependency inject. And then we can remove the run, test, and separate processes annotation, and our tests will be much faster. So this is our original function. It doesn't use dependency injection. It's creating a dependency all by itself. And we're going to inject it. So all injection means is that you're getting a dependency from somewhere else. And in this instance, we're going to pass it as a function parameter, weather forecast weather, and we're going to give it a default value. It's important, if you're refactoring legacy code, to give it a default value, because this means you don't need to change the call signature anywhere else. If something is calling get outlook, it doesn't need to pass it a dependency. It's fine. It can still run. It will still work. Then instead of creating our dependency within our method, we're going to use the given injected dependency if it exists. And if it doesn't exist, that's fine too. We'll just go ahead and create a new one. So the code has been refactored to use an injected dependency, but it doesn't require one. the functionality has not changed. Our code still works in exactly the same way. But now we have the potential to inject our own dependency. So looking back at our test, we got our test half full. We have our overloaded weather forecast. We have our returning the weather is sunny. We're going to remove that overload. We don't need it anymore because we can inject this dependency instead. So we're just going to mock and pass it the class name. We've got the colon class. It's like a magic way of basically PHP getting the name, the fully qualified name of the class. It's easier than typing out this string and then if you change the class name. Anyway, so no overloads. Now we've had that mock forecast, we're going to inject it. We're going to give it to our getOutlet function. And our outlet function is going to now use our mocked dependency. Hooray! Now our tests are going to run much faster, and you've all learned what dependency injection actually is and what it actually means. And it's not that hard after all. You can all go away and you can deal with that. So, you have to take a sip of water. This is our third tricky test scenario, ungraceful exiting. What does this mean? It means when you have something like this, if you have a redirect in your code, as we have here in my get me out of here function. If I'm a celebrity, I'm going to redirect myself to Google because I don't want to be on this stupid application anymore. Otherwise it's going to say, no, you've got to stay because you're not a celebrity. Okay, fine. But what happens when you try to run this as a test in a test suite? We have, again, a few branches. We're either going to get us out of here because we're a celebrity, or we're going to not get us out of here because we're not a celebrity. You'll find that you'll have to run the test in separate processes again because we're setting headers, and the test runner has already output. So when you have a location header, it sets the header on the PHP output to something, but it's going to break because the output's already been sent. It can't send a header on something that's already been sent. So if you run in separate processes, it's going to, again, go through each test in a separate process every time for your headers to be set properly. So when we have our test leave me here, it's going to say no, and that's fine. Cool, we can just run the get me out of here function and assert that the result is no. But when we are a celebrity, it's a bit weird because our test runner can't actually redirect us. It can't actually set a redirect. It can set the header, you can try, but it's not going to get anywhere because it's in a test runner. So when we try and test get me out of here because I'm a celebrity, it still gives us no. It still equals no. It will do the header and then continue with the function and return no. Yeah, but it would get me out of here. So that's kind of a failure, isn't it? So you have to look at the way your method is continuing after you're setting something like a location header. There are two methods to refactor this, and I would say both are fairly safe. You can either return, or if you're in a loop, continue, or if you're in a switch case statement, the break after you set your headers so that you don't accidentally continue executing the code after the point at which, in a normal situation, the user would no longer be within that process flow. Or, alternatively, and this is just sort of flipped round version of the first option, is to only perform only set the location header at the very last point in your code. So here I've done the first option, I've just put a return immediately after setting the location header. That way, once it's purportedly redirected, it's returned. Nothing happens, doesn't go any further, you're good. Or this is the flipped round version, is it's going to return note as soon as feasibly possible. So we're not waiting to the end to perform the return. And what is at the end is the location header. So the location is only changed at the very last moment. And so that's a fairly safe way to refactor that. And here we have our test. And hooray, it works. We don't get a no anymore. So this is another thing that I've actually encountered, is the use of exit. I couldn't resist the topical reference. So anyway, this is our Brexit function. If you're a Remainer, which I am, it will return the string people's vote. Okay. If you're not a Remainer, it'll exit completely. It will crash and burn and die. So how do you even test this, right? Because, all right, we've got our two branches again. We're going to test the Brexit, and we're going to test if we remain. Remaining is pretty easy. We call it the Remainer true, and we get people's vote back. Hooray, that works. Testing Brexit, it never happens. Yeah, because it's gone, it's exited. Not only does it exit this method, it exits the whole test run. The entire suite just goes kaput. So how do you test it? How do you test if this works? How can you even test this function? This is really annoying. So we're going to do a bit of refactoring. And again, hopefully, this should be fairly safe. We're going to create a wrapper around the exit functionality. We're going to delegate it to someone else and let them handle it. And then we're going to use our trusty friend dependency injection again. And we're going to refactor it to use that injected wrapper. And we're going to mock the exit wrapper. So this is our Brexit utility. It has one method, Brexit means Brexit. And it completely exits, as you would expect. And then we're going to use our dependency injection. We're going to add a new parameter, and again we're going to set a default of null. This is important, so we don't have to change the rest of the calls to this function. And if we didn't pass one in, we're going to create one ourselves. This is our argh dependency. It's got injection. These are the sacrifices we have to make for legacy code. And instead of exiting, we're going to use our utility function Brexit means Brexit. So when it gets there, it will exit, and it will exit completely. And we're going to mock Brexit, because we don't actually want it to exit, because that breaks our test run. So we're going to mock our Brexit utility, and we're going to do nothing. We're just going to ignore Brexit, we're just not going to do. It's not going to exit, nothing's going to happen, you're going to go around in circles forever. We're going to use our mock Brexit, and success, it works. We don't get people's vote, the application doesn't crash and burn, everything's great. So I hope that you enjoyed that Brexit thing. This kind of wrapper technique can be used for all sorts of functionality that's built in to PHP. Randomness, for example. Yeah, it's a good technique. Take a tricky test scenario number 4 is the file system. So have you ever been in a situation where you need to test a function that modifies files on the system? Sort of like when you're trying to make a hit counter, because you're in the 90s. So we've got a function that counts a hit, so that when this function is run, it gets a text file and it increments the text in that file. We're going to test it, and when we run count hit, that's fine. We get our hit counter file, we look at its contents, we save that as the count prior to the hit count being called, and we get the contents again afterwards, with some semicolon. And then we assert that the previous value, the new value is now the previous value plus 1. And that is a test that works, but it has a side effect. Every time you run the test suite, it's going to increment our hit counter, and your metrics are all going to be wrong. So we need to refactor this, and again we're going to use our amazing dependency injection. And we're going to create a test hit counter file. And then we're going to reset the contents after each test run, so that we've always got a nice blank slate. So again, with the dependency injection, we're going to inject our file and use it. And then we're going to create a hit counter file. There's a test hit counter file. So this is a completely different file, but that's okay because we can use it. And our hit counter will use that file instead of the regular file that it was given previously. And then in our teardown, as PHP unit provides us, we can reset the counter to 0.
That's all good and well, but you've still got to maintain that file. You're still touching the file system. And that is not always advisable. It's not always possible, depending on what system you're running. So there is another way, and it is the fake file system. There's a package called VFS stream, which is a virtual file system, which you can use to mock the file system. And it works really easily. So this is our original test. And you see if we've got our file name here, and we're using get file, get contents, file, put contents. And this is what the same test would look like using the virtual file stream. So first of all, you have to set up your virtual file stream. That will create a mocked version of the file system. And within that, you can create a new file. We've created a new file, and we've given it a name. We've told it where we're going to put it in this fake file system, and we're going to set the content to 0. So we're always going to start from 0. And then we're going to count here, and we're going to inject our file. And then we're going to just check that it equals 1, because we always know that when the hit count is run, the new count should be 1 because we started at 0. So that is how you would mock the file system. We don't need this anymore. Yay, less code is always good. The tricky test scenario number 5, spaghetti code. So spaghetti code is quite difficult to define. It's usually something that's more process-oriented rather than object-oriented. It has lots of side effects. So this is an example of spaghetti code, is when I'm eating bolognese. I have bolognese, it's not eaten at first, I have a plate of bolognese, it's not been eaten yet. I can eat it, and I can also check whether it has been eaten. But when I eat it, I need parmesan on it. I can't eat it without parmesan, and I also have to have garlic bread. This is kind of arguably something that the bolognese should not be concerned with, but this is legacy code, and it is concerned. The bolognese is concerned that it must have parmesan, and it must have garlic bread. So this is our spaghetti code. This one eat method becomes unnecessarily complicated. So how are we going to test this? This is fine. We can have a new bolognese and we can eat it. And that's going to return true. When it's going to get is eaten, it's going to be eaten. But we're not testing any of the side effects. So there's a couple of ways that you can approach this. There's a covers annotation in PHP unit, which allows you to specify what exactly you're attempting to test with this. So you can tell it, I'm only interested in testing the bolognese function itself. I'm not interested in testing the garlic bread or the parmesan or anything like that. We can just ignore those completely. So that when you run your code coverage report, it won't tell you that you've tested garlic bread when you actually haven't, because you've just tested bolognese. It makes your testing a bit more intentional. And I like to personally create reasonable expectations to illustrate the different scenarios and the different processes that go on within my test, and I can form assertions and expectations on those processes. So this is our test. So I want to write 2 new tests, and I'm going to try and eat the bolognese that's already been devoured and figure out what should happen. And if there's a new bolognese, I want to see what happens when I eat it. So I have my new bolognese, one is eaten, one is not eaten. And I'm going to test the garlic bread in this instance. I'm going to see that when I receive a bolognese that has not yet been eaten, that I do in fact also eat garlic bread. So we have I've created a new function here called expect garlic bread to be eaten, which creates a mock overloaded version of garlic bread because we're not using dependency. And at some point during the process of my executing or eating of the bolognese, I should also have eaten garlic bread. So garlic bread should receive eat. And then I can use this in our 2 functions to demonstrate our diverging paths of processes. Test the devoured bolognese. I can eat it, and I don't eat garlic bread again, because I've already eaten garlic bread with my last bolognese. But when I eat an uneaten bolognese, I do in fact also eat garlic bread. This is my last one. Tricky test scenario number 6, private methods. Who here has encountered a private method that they feel like they need to get covered with unit tests like this? Can't touch this. And you end up with something like this. I want to test the can't touch this function, I create a new dependency hammer, and I can't touch this, but I can't because I can't touch this. It's private. So you can't test it. How can you test it? Don't test it. Just don't. Private methods are implementation details. They should be able to be ignored. They should be invisible to the public API that your application exposes. So instead of testing the private methods themselves, you should test the public methods that use them, which in this case is our stop method. So our stop method calls the can't touch this, and we look at the result of that instead. And indeed, the result is hammer time. And by proxy, we've tested our private method. We don't need to test it any further. It's been covered. It's an implementation detail. It works. We're good. That is it from me. Does anyone have any questions?